Welcome back to topological data analysis. Today we will talk about clustering via persistent homology. On Friday we will talk about finding holes in data, and then on the following Monday you'll be able to create your own homology, get your own homology named after you. So that will be the next few lectures. But today we'll focus on clustering. I'm going to start by quickly reviewing how to create a simplicial complex. Hopefully you've had a chance to listen to those preparatory lectures, but if not, listen closely today. We start basically with our data. So we've got a bunch of data points that I've got pictures in terms of vertices, but you don't necessarily have to have them being points in Rn. You just need some data points. Then our next step is to add our one-dimensional edges based upon some idea of closeness. In this case, I've got them plotted so I can measure the distance, but as long as you've got any idea of closeness, that will work. We have to, though, be specific about closeness, so we will choose a threshold and we will connect an edge if the distance between our two vertices is less than our threshold. And so in this case, I chose 1.8 centimeters. So anything where the vertices are of distance less than 1.8 centimeters, we will join them all up. So lots of things that we can join up via edges as long as their distance is less than 1.8 centimeters. So that's how we come up with the one-dimensional simplicial complex, but we can then create the Rips complex. And so for the Rips complex, the Vietoris-Rips, we just now add all possible simplices of dimension greater than 1. So if I want to add a two-dimensional simplex is a triangle. So as long as I've got 3 edges forming a triangle, I can go ahead and add my two simplex. If I have something forming a square, that's not a triangle. We actually need 3 edges forming the triangle, so we can't just do topologically a triangle. It depends upon the 3 edges existing. 4 edges is not the same as 3, and so I can't fill in this square unless I add an additional edge, and if I add an additional edge, then I can fill in the 2 triangles to get a square. So I can fill in lots and lots of triangles, so you can fill in these triangles. I don't have to if I'm just creating an arbitrary simplicial complex, but if I'm doing the Vietoris-Rips simplicial complex, and frequently just called Rips for short, then if I have 3 edges that form a triangle, I am required to fill it in with a 2 simplex. And we go higher if I have 4 2 simplices forming a tetrahedron, or in other words, if I have 4 points that are close to each other, then I fill it in with a 3 simplex. And so if I have 4 points close to each other, then I have 4 vertices along with all the edges because they're all close to each other, along with all the faces, along with the 3 simplex. And we can continue up in dimension. You don't have to be able to actually draw this. We just say that if I have 5 points that are close to each other, then I have all the edges, I have all the 2-dimensional faces, I have all the 3-dimensional, so I've got a 3-dimensional tetrahedron in here, another 3-dimensional tetrahedron, I've got lots of 3-dimensional tetrahedrons, these ones down here, and I also have the 4 simplex. So the 4-dimensional thing, which I won't try to draw, we'll just say it exists, and this 4 simplex, all it does is it tells me that I've got 5 points that are close to each other. So that's how we create our Vietoris-Rips complex. There are other complexes which we may discuss later, but I basically want us to get as quickly to being able to use the persistent homology software. And also many of the articles, most articles will actually use these Vietoris-Rips complex when you're doing persistent homology. It makes sense that, we want to denote when 5 points are close to each other, so that 4 simplex gives us that information, and it is also very nice for computational purposes. So any questions about just creating our simplicial complex? So we also have to, though, decide what our distance is. We can actually use balls to measure our distance. So if I increase these vertices to become balls, well, if now my two balls intersect, if my radius is half the threshold, then if two of my points are within that threshold, then these balls will intersect, and so I can determine when to draw edges based upon whether or not the balls intersect. So I can have lots of balls intersecting, and so I can still get my three simplex, all my faces, etc. And so we can create our Vietoris-Rips complex based upon the intersection. But we're not, for those who know check homology, we're not doing check homology. We could, but we are doing the Rips complex where whether or not the three balls intersect, we will still fill it in with a triangle. So there is another type of homology where we would not fill this in because we didn't have an intersection among the three balls. But it's a nice pictorial way of, instead of getting out that ruler, having the balls makes it easy to see when I should be creating edges. And if I've got the edges, then I can get my higher dimensional simplicities. So 2 points are close, i.e. we create an edge if they're corresponding balls of the radius being half the threshold intersect. But the question is, how do you choose the radius? Well, if you don't know, you can use balls of varying radii. So I can start off by increasing them a little bit. Now, these things kind of intersect, so I might get an edge between these two vertices. I can increase my radius a little bit further, and I can see I've got more edges. So at each of these center points, there is a vertex, and if the balls intersect, we'll go ahead and do the edge, and we can continue increasing and, continue increasing until the entire page is purple if we so choose. The classic paper on this is by Edelsbrenner, Letcher, and Zamorodyan, probably pronounced better than I'm doing, on topological persistence and simplification. So that's the classic paper that you might want to take a look at that introduces persistent homology. I'll put some links to some other papers as well. There's basically 3 groups who did something similar at the time. To motivate, however, I like to motivate with biology applications. So to motivate this persistent homology, we're going to very briefly discuss this 2011 paper on discriminative persistent homology of brain networks. So basically, they looked at this brain data for 24 children with hyperactivity, 26 children with autism spectrum disorder, and then they had a control group of 11 children. And they basically measured the glucose utilization at 97 different regions of interest. So there's 97 regions of interest in this particular study. So we've got points within the brain. Now, we're actually not going to care about the location, so the distance is not going to be based upon the location where it is in the brain. The distance will be based upon the correlation between the glucose utilization. So if glucose is utilized here and here at the same time, at about the same rate, then we will correlate these two. So it doesn't matter if these points are far away, we can still have an edge between these 2 points if the correlation among the glucose utilization is, well correlated. So that's how the edges will be the distance function in this particular study. But the question is, how do you use the threshold? There's a lot of question. Different people do it differently. There is, science behind choosing the threshold, but it's not all that well developed. Plus, checking out a variety of different thresholds will be helpful. One can go ahead and create the Vietoris-Rips complex, and that's what I'll be, saying. But in reality, for this particular paper, they were just looking at clustering. They have discussed in the future looking at holes as well. But in this particular paper, they're only looking at clustering. Well, for clustering, I don't actually care if there's a triangle. These 3 points are clustered together as long as they are connected. So whether this thing is filled in with a triangle or whether it's not filled in with a triangle, it's still clustered. So the pictures you'll see will just be the graphs. And so we actually only need the graphs, you only need the vertices and the edges if you're only interested in clustering. So let's take a look at some of the results. Well, if you choose different thresholds, you might have something where you might start off with basically almost everything being connected. So this is sort of the correlation where if it's red, well, basically region 1 is correlated very nicely with region 1. Being the same region, you'll always have just that. We're not going to do loops, but we do have that along the diagonal, it's nice and, bright red. And then we have other regions where this region is correlated. So this region here is correlated with this region up here. So both our x and our y axes are basically the same. So if you take this column, which you can't really read, sorry it's so small, but you can look at the original paper, if we've got the same rows as columns. So I can see this is the frontal region, so this will be the frontal region column here as well. And so I can see the frontal region is correlated somewhere around I think it's the occipital region, kind of hard to say, it might be the parietal region. So there's a correlation between these two. And so if they are correlated, we do an edge. In this particular, for these graphs right here, for the 3 different groups, we've gone ahead and said, even if they're mildly correlated, we'll go ahead and put an edge. So we actually start off with lots and lots of edges. So we'll go ahead and start off with, 100% edges, everything being connected. And then as we, so in that case, our ball might have radius infinity. And then we decrease the radius of the ball. So we decrease the radius of the ball, and we'll have fewer and fewer edges as we decrease the radius of the ball. And so we'll have fewer and fewer edges until we have no edges down to where, the only thing that correlates with is the region with itself, so we might have absolutely no edges down at the opposite. So having lots and lots of edges, everything's connected over on this side, down to very, very few edges as we decrease the radius of the ball. Frequently, when you see these graphs, they will be drawn in the other direction, but for here, we're decreasing the radius of the ball as we go in this direction. And you can see, if we just take a look at the number of edges, as we decrease the radius of the ball, well, the percentage of edges that are, that actually exist, well, are different for our ADHD, our autism spectrum, and our pediatric control. You can see that for our ADHD, the number of edges decreases more rapidly. So you actually notice something when you look at persistence. We can see there's a difference between these 3 different groups. Here it decreases very rapidly for our ADHD versus for our pediatric control, that's this one right here, it decreases far less rapidly. And our autism spectrum is between the two. We can also look at another simple graph theoretic property, and that would be just the number of connected components. Well, in the beginning, when you have lots of, so that would be this red thing right here, so this red one right here, we can see that in the beginning, when you have lots of edges, you're going to have basically one component. So in the beginning, we just have one component, so one component, and then it starts going up, and then it goes up more, until we have 97 different components when our radius is 0. And you can see that the number of different components changes depending upon which group you're in. We can also take a look at another graph theoretical property, and that is small worldness. Small worldness is basically how close is your graph to the ideal small network graph. If you've heard of 6 degrees of freedom, that has to do with your small network. So if we are the vertices and I draw an edge connecting the two of us, if we know each other, then the 6 degrees of freedom says that there will be, on average, a path of length 6 connecting any two random people. And so that's what a small world network is like. And so the degree of small worldness is a property that you can also measure, and you can see that that changes differently. So we can look at various graph theoretical properties and see how they change as we decrease our radius, so going from infinite radius to 0 radius over here. But we can also say there are different types of graphs. So for example, there are random graphs. A random graph is basically if I had 97 vertices and I chose some probability, maybe I'll choose 50% or maybe I'll choose 100%, depending upon what I want to choose, and I will connect a pair of vertices with that probability. So if I'm choosing 100%, all the pairs of vertices are connected by an edge. If I choose my threshold to be 50%, then if I choose a pair of vertices, then I will flip a coin to determine whether or not I connect that pair of vertices with a graph. We can see that in the beginning, if I have a very large radius, well, things are basically connected randomly. So we've got so much noise in our data that we're not really getting anything significant out. It looks like a random graph. As I lower my radius and increase my threshold, we now get into something that looks basically small network. So where there basically is normally a path connecting a pair of vertices, but not normally an edge, and it basically looks like a small network graph. There are many different types of graphs. This is one type of graph, and so at some threshold it looks like that. But if I increase my threshold or decrease my radius, I now get something that's called a cluster network. So that's another type of graph. So depending upon your threshold, it doesn't just change your graph theoretical properties, it changes the type of graph as well. So it creates a very different type of graph with very different properties. And so choosing your threshold can, two different papers, if they choose a different threshold, based upon good reasons, can come up with very, very different results. And so that's why looking at persistence is a nice thing to do. So if we do persistence, in this case, our Betty naught, so frequently we use the Greek letter Betty naught, that's just the number of components or the number of clusters. So it equals to number of clusters. So in this case, we're going in the opposite before. We're starting off with you can see here we start off with basically nothing connected or very little connected. So at 0, our radius is 0, and we have 97 different components because nothing's connected. We move up a little bit, and so at this stage right here, that's this thing, we see that there are a few edges, and so we've reduced the number of components to somewhere along maybe 90-something. And then as we increase our radius, so now we're increasing our radius as we go, so R is increasing. So as I increase the radius, we get more and more edges, so more and more edges, and you can see, finally at this stage, we've got lots and lots of edges, and we can continue. We know what happens as we really increase. We just get one component and everything is connected. So that is our Betty naught, which is the number of components, the number of clusters, dependent upon our threshold. As we increase our radius, more and more things are connected, and so we get fewer and fewer components. One thing you can notice about this data is the number of connections changes at a different rate for ADHD versus autism spectrum versus your control. So the number of components, the number of connections changes. So if I'm at point 2 here versus if I'm at point 2, no, we don't have as many connections here. So we've got a lot more components among ADHD than we do. Here we've got far fewer components and a lot more connections. So connections form more quickly for our pediatric control than it does for our other two groups in this particular study. So that can give you some good information about what's difference between these brains and could potentially be used in diagnosing ADHD and autism spectrum disorder. So that's basically the motivation. Any questions about the motivation for our persistent homology? And remember, you can always type in questions or you can ask them verbally. So we should have yes, we do. I think everybody can speak. But you can also type in questions too, so either way works when you have questions. Well, I have one question, so we like this, hopefully, so all of us like this. How do you compute it? So we want to know, how do we compute beta naught? How do we compute the number of components? We know how to create our simplicial complex. I'm going to start off with the simplicial complex now. We know how to create our simplicial complex. If this is our simplicial complex, I should have moved these points a little further apart. Maybe I'll do that before posting these slides. So we now have this particular complex, and I just want to count the number of components. Well, that's easy. I've got one component here, it's 2. Well, the thing is, I don't want to do it by eyesight. I want a computer to do it because, here I just have a few vertices, edges, and faces. If I've got a large data set, we had 97 vertices in the simple brain example. That's actually one of the simpler biology examples in terms of number of vertices. So many times you have way more vertices depending upon your application. So we want to think computationally, how can we get a computer to do it? Well, one of the things is it helps to have a language. So for example, I can talk about C naught being the free vector space generated by all my vertices with Z2 coefficients. We can actually use any coefficients, but this will be sufficient for our descriptions today. And we can have C1 be that generated by all our edges. The reason we might want to do that is because if I want to do the boundary of E1, in shorthand, we'll use boundary of E1. Well, my boundary of E1 is the vertices V1 and V2, so I would like to be able to use the formal sum V1 plus V2 to denote that the boundary of E1 is V1 plus V2. So it's just a nice simple notation so that we can easily denote the boundary. Yeah, there are other ways I could have denoted the boundary, but this is a nice way of denoting the boundary. So my boundary of E1 is V1 plus V2. I did say formal sums with Z2 coefficients. So my coefficient for V1 is 1, my coefficient for V2 is 1. I have 0V3 plus 0V4 plus etc. So for our purposes in terms of clustering, Z2 is perfectly good because all I need to know is, do I have it, in which case I have a coefficient of 1, or do I not have it, in which case I have a coefficient of 0. So with our Z2, our only coefficients are 0 and 1, meaning we either have the element, so we've got 1v1, or we don't have the element in our boundary or whatever we're talking about, in which case we have 0. So Z2 is great for, it's good computationally and great for clustering, for finding the number of components. Any questions on that? So now let's go ahead and start clustering. Let's take a look at the component containing V1. So think about, what if you were a computer? Well, we could start with, I want to take a look at the component containing V1. I can then notice that I've got my edge E1, so I can look at my boundary of E1 is V1 plus V2. Well, that means E1 connects V1 to V2. So if I've got an edge as a boundary of E1 is V1 plus V2, I can throw V2 into my cluster because it's connected. It is in the same component. I can see that via the edge E1. I can also take a look at my edge E2, and I can see that is V2 plus V3, so the boundary is V2 and V3. So in other words, V3 is connected to V2, so thus V3 should be in the same component. And I can see that there aren't any other edges, but I'll just put a line here at the moment because I'm a computer. I haven't looked at things yet, so I can't use my eyesight. So now we will see, is there anything else connected to V1, V2, V3? No, there's nothing, so we will go ahead and close it off, and that is one component. Now let's go ahead and take a look at V4, and so I'll throw V4 into a different component. And I can see that E3 edge emanates out from E4. I can notice that the boundary of E3 is V4 plus V5, and so I've got these connected, so they're in the same component. Boundary of E4 is equal to V5 plus V6, so V6 is in the same component as V5, and so we can throw in V6 here as well. We can say that we've now looked at all the vertices, but another algorithm is I can just take a look at all the edges instead. So I could just look at boundary of E1, so I can just go through all my edges, my computer program. There are more sophisticated ones, but I can write a program that says boundary of E1 is V1 plus V2, so I throw them into the same component. Boundary of E2, get them into the same component. Look at E3, E4, and E5. Just look at all the edges and just make sure that all my vertices are in the same component if there is an edge connecting them. And so that is one simple algorithm that will determine our number of components. Notice I did not need the face. So this face was completely immaterial when you're counting the number of components. On Friday, we will look at holes, and then our faces will be very important. They're two-dimensional faces. But basically, when you're taking, depending upon what your dimension you're looking at, if we're looking at number of components, then all we need are one-dimensional edges and our zero-dimensional vertices. So that is the idea behind calculating the number of components. And that's sufficient for calculating the number of components. We can write a program that will do that pretty quickly. But we would also like to generalize this to when we want to find holes. So now we're going to introduce a lot more notation, much of which is actually not needed for the first homology and counting the number of components. But it will be needed when we start taking a look at finding the holes, and so we will introduce that notation here. So, but first we'll note that these are our components by using our boundaries. So in terms of our notation, we will start off with C0 just being the set of zero chains. A zero chain is just a formal sum of our vertices, and because I'm using Z2 coefficients, my ni's will all be either 0 or 1. The coefficients will either be 0 or 1. And so I'll just have a formal sum of my vertices. For example, the boundary of E1 being V1 plus V2. My C1 will be the formal sum of all my one-dimensional simplices. We can do Cn being formal sums of our n-dimensional simplices, but for number of connected components, we only need C0 and C1. And then the other thing that we had is we had this boundary map that took our edges and said what vertices we had. So let's take a closer look at our boundary map. So in our boundary map, we said that we had boundary of E1 was V1 plus V2. So that's actually telling me my map. It's telling me that E1 gets sent to V1 plus V2. So the image underneath my boundary map of E1 is just its boundary, which is V1 plus V2. The image of E2 is just its boundary, V2 plus V3, etc. But remember, C1 is formal sums of my edges. So I have to say where an arbitrary formal sum goes. So I want to know where the boundary of E1 plus E2, for example, goes. So what is that? What is its image? Well, I'm hoping its image is going to be V1 plus V2. We hope it's V1 plus V2, because if I take E1 plus E2, doesn't it look like that should be its boundary? Well, it is when we use formal sums and extend linearly. So if I want to do the boundary of E1 plus E2, if I want to do the boundary of E1 plus E2, I can do the boundary of E1 plus the boundary of E2. So we just distribute our boundary across our E1s. If we had any scalars other than 0 or 1, we could pull out the scalars, our coefficients, but we don't have that, so we can just distribute our boundary across the sum. That's what it means to extend linearly. And so now I have boundary of E1 is V1 plus V2. My boundary of E2 was V2 plus V3. And so I get V1 plus 2V2 plus V3. But we are working with Z2 coefficients, so we were working over Z2. So we're working mod 2. So the only two numbers we have are 0 and 1. All the even integers are equivalent to 0. All the odd integers are equivalent to 1. So if I've got 2 of something, that's equivalent to 0 mod 2. And so we have V1 plus V3 mod 2. And so we get exactly what we want. We get that the boundary of this thing here is V1 plus V3. Any questions about that? Just to take a look at a couple of other examples, we could also take a look at the boundary of E3 plus E4 plus E5. E3 plus E4 plus E5. Well, what do you think that boundary is? Does a circle have boundary? It doesn't, so I'm expecting to get 0, and sure enough, if I extend and get boundary E3 plus boundary E4 plus boundary E5, I'll write my E5 a little neater. So I could have done 2E4 as well, but that would have been equivalent to 0. So I want to do E3 plus E4 plus E5. Well, the boundary of E3 was V4 plus V5. Boundary of E4 is V5 plus V6. The boundary of E5 is V6 plus V4. Well, that means I've got 2E6. That's equivalent to 0. So whenever I've got a pair of something, I can just cancel them out. 2E5 is equivalent to 0. 2E4 is equivalent to 0. And so my boundary is 0. Any questions on that one? That's an important one because we're going to be looking for cycles. We're going to be looking for holes. And while this one is filled in, if it weren't filled in, we would have had a hole. So that the boundary of this cycle is 0 is a good thing. We can also do the boundary of any formal sum. My coefficients are 0 or 1. So I can either choose E1 or not. I can choose E2 or not. I can choose E5. I can talk about the boundary of any of these things. We just extend it linearly. The other ones were more interesting, but here we also get that we have V1 plus V2 plus, for E5, V4 plus V6. So we also have that as well. So the next thing we want to do is actually extend out this map. We're actually will be extending a lot more later on, going up into higher, but we want to go ahead and say, how are we going to denote the components? Well, remember we used our vertices to denote the components. So our vertices are C0, and the thing that we will use to denote our vertices is we want to do our boundary for our vertices. Well, what's the boundary of a vertex? The boundary of a vertex will be 0. So if I take the boundary of a vertex, whatever that vertex is, I will get 0. And so if I say Z0 is the kernel, so that's just the map term for saying everything that gets sent to 0. So if I take a look at everything that gets sent to 0, well, it's everything. Every vertex doesn't have boundary, so my kernel is everything, so my Z0 is the same thing as my C0. It will be all formal sums of all my vertices. Their boundary is all 0, and we will use that to denote the number, we'll use sets of vertices to denote our connected components. We also will call these cycles. They're actually 0 cycles. So that'll make sense later on, because when we do our boundary of C1, this will be a 1 cycle. And so we can also have 0 cycles, 2 cycles, just things that don't have boundary, where the boundary is 0. And so computing our kernel in the case of Z0 is very easy because it is absolutely everything. None of the vertices have boundary. Any questions there? Then we also need to, so we know we were going to use our vertices to indicate our connected components, but we needed to say what is actually connected, and to determine what's connected, then we use the image. We use the image over here of all our boundaries. So we use the image. If I took an arbitrary cycle here of my E sub i's, I looked at the image of that. So it was that image that we were looking at. That was what determined whether or not things were connected or not. So the fact that there was an edge connecting E1 said that V1 and V2 were the same. The fact that there was an edge connecting V4 and V6 said that they were in the same component. So we can now actually create our first homology. So our first homology is to take our cycles mod our boundaries. And that's really what we did in the beginning when we were doing the informal counting the number of components, is we can start off with our with all our vertices. So we'll start off with all our vertices, and then we'll start collapsing and saying, well, V1 and V2 are in the same component. And so we will use this notation to say that we're going to set V1 plus V2 equal to 0 to say that they're in the same component. So we'll say that V1 plus V2 equals to 0. So therefore, V1 equals to minus V2. Oh, wait a minute, I'm working mod 2. Minus 1 is the same thing as plus 1. All odd numbers are equivalent to 1. So I've got V1 equals to V2 mod 2. And so I can use, this is just the notation that we're going to use to be able to say that V1 equals to V2. And by equal, we just mean it's in the same component. So our equal means in same component. And so this is sort of the notation that we can use. So in our computer, we can go ahead and put in our list of vertices. We can put in our relations. So these right here are our vertices are our generators. And here are our relators. And we have that we can use this relationship to say that V1 and V2 are in the same component. Because we're working with formal sums, summation n sub I, V sub i's, it's nice to have the actual equality here, because then I can get that V1 equals to V2. And so if I've got the summation, if I've got the summation, if I've got N1 V1 plus N2 V2 plus etc., well, I've now put this thing in the same component, so I can now call this N1 V1 plus N2 V1. So I'm now using it as a representative to represent the component. So in this sort of thing, I'm trying to just represent the components, not the vertices. If I were to do the vertices, I'd be sticking with C0. My zero chains, I'd be sticking with V0 if I wanted to work with vertices. But now I want to work with the components, so I want to mod out by things. I want to say that V1 and V2 are in the same component, and so if I want to denote the component, then these two things would denote the same component. So whether I had V1 or V2, it's the same component. Okay. So we do frequently, mathematicians are lazy, so instead of writing equal to 0 each time, we frequently just drop that. And we'll just write V1, V2, and we assume everybody knows that we've set them equal to 0. For today, I'll go ahead and keep the equal to sign, but often we will just go ahead and say they are equal to 0. In most of the papers, you'll actually store this information nicely in a matrix, and we will possibly get to the matrix form today, hopefully. So going back to this sort of thing, we notice that V1 plus V2 equals to 0, so that gave us V1 equals to V2. So that means I can get rid of V2, because since V1 equals to V2, I can now, in my computer program, I can start taking my vertices here and using my relations. I'll use this one first, to say that I don't need V2, I can get rid of V2 because it's in the same component as V1. So this is the same thing that we did before when we said, oh, we'll start off with V1, and then we'll throw V2 into the same component. But now what I'm saying is we're going to go ahead and use V1 to represent V1 to represent everything that's in the same component. So I don't need V2 because V1 will represent that component. And I can get rid of this equation, well, except for I need to note that since V1 equals to V2, I can note that I can change this to a V1 right here. Since V1 equals to V2, I can change that to a V1. So I now have this thing right here where I kept my V2 plus V3 because I know that since that V3 is in the same component as V2 because of this equation. But remember, V2 was in the same component as V1. So because my V1 was in the same component as V2, wherever I saw a V2, I can change that to a V1. So we now have, it simplifies to this thing right here. Well, I can continue simplifying. V4 is the same thing as V5 in terms of being in the same component. So I can get rid of, I skipped this one, let's do this one first. So we know that V1 is in the same component as V3, so I can say that, use this thing to get V1 equals to V3, thus I don't need V3, and I've now used this relation so I can get rid of it. Once I've used the relationship, I don't need it anymore. Similarly, V4 and V5 are in the same component, so that's what this thing right here says. So I can get rid of V5, and I've now used this information, so the computer doesn't need to use it anymore. We can get rid of it. Same thing, we've got V5 and V6, so I've got V5 plus V6 is in the same component, so I can get rid of V6, and I can get rid of this relation right here now that I've used it. I now have the group generated by V1 and V4 subject to V4 plus V6 equals to 0, but remember V4 was equal to V6, so I can actually put a V4 here. Well, what's that equivalent to? This is V1, V4, such that 2V4 equals to 0.
But what's 2v4? 2 is equivalent to 0 mod 2, so this is the same thing as v1, v4, subject to 0 equaling to 0. So this last relationship here, once we canceled everything else out and noticed that v6 was the same thing as v4, just gave me the relationship that 0 was equal to 0. Well, I know 0 equals to 0, so I don't have to write it down. And so thus, this is my first homology group. This is my H0. It is generated by these two components. So since it's generated by these two components, I now know that I've got, and no additional relationships. We've gotten rid of all the relationships. We now know that this is what our H0 is. So any questions about that? So that's how we calculate homology, whether it be the first, second, third homology. When we're doing the number of components, we're doing the zeroth homology. When we're interested in clustering, we still do our cycles mod our boundaries. And so our cycles, in this case, it's generated by our vertices because they all get sent to 0. And then our boundaries, we can just do our boundaries of E1. It'll be generated by the boundaries of our EIs. I could have thrown in boundary of E1 plus E5, but that would have just given me the relationship after I've applied all the others of 0 equals to 0. So I don't need boundary of E1 plus E5 because that will be, I know that boundary of E1, I already had that in my relationship. I already had this thing in my relationship. So adding the additional relationship would not have given me additional information. So that's what we have for our H0. And so we have that our H0, this is our H0, is generated by these two components where I could have kept track that my V1 contained this component, my V1 represented this component, and my V4 represented this component. For those of you who know about equivalence classes, we have just partitioned our set of vertices. We've just partitioned our set of vertices into two equivalence classes, our two components. And we know what's equivalent to V1. I could have used a different representative. So there's lots of different representatives I could have done. And that does mean, depending upon how you enter the data, you can get different representatives. So that's actually a bit of a weakness in terms of this computational thing, is often you now want to find a nice representative. And the question is, how do you find a nice representative? Well, in terms of the vertices, you probably don't care which vertex. You might, in which case you have to put in your data nicely or program it in nicely. When it comes to cycles, you might care, and there's a whole different other thing that tries to find nice cycles. So we'll mention cycles a little bit more later on. But we do have 2 minutes for our last slide, and that is to use our matrices. Many of you are familiar from linear algebra that I have a set of equations here, and this set of equations I can translate into a matrix. And the matrix in standard linear algebra would be that we would use our columns for our variables and our rows for our equations. And so I'd have V1 plus V2 is 0, V2 plus V3 is 0, and I would do that. However, for what we're doing, it's easier to use the transpose. So we're going to use the transpose of the standard linear algebra. And so when we do our matrix, we're actually going to put our vertices on this as our rows, and our equations, which come from our edges, which will be our columns. And so the equation V1 plus V2 equals to 0, we'll get 1, 1 right here. Our equation V2 plus V3 equals to 0, we'll have 1, 1 for the second column. Again, in standard linear algebra, that would have been a row, but we'll just go ahead and do the transpose of what we do in standard linear algebra. And so our equation corresponding to E3, the boundary of E3 was V4 plus V5, and so we can do V4 plus V5 I can also represent the boundary of E4 was E5 plus E6, and I can also represent my edge by the unordered pair, V4, V6, so that would be my edge E5, in which case I also have a 1, 1 for my last column here as well, and so we can do matrices and do both row and column operations, keeping track of how it affects our basis of our V sub i's as well as our E sub i's, and use that. And that's generally how many of the programs actually work. If you think about it in terms of matrices, it does simplify that. So we will finish up our zeroth homology on Friday. It won't take long to do our matrix. And then we'll go ahead and do our first homology and start looking at holes in data. So, any questions from today? So, see you on Friday.